Lately, I've been spending a lot of time designing and building a remote control. And in this video, I'm excited to take you through how it all started, the mistakes I made, and the lessons I learned along the way. So, let's get started. This video is sponsored by pcbway. If you are familiar with the ESP32, you probably already know that it's capable of handling both Wi-Fi and Bluetooth functionality. And if you are using the ESP Now protocol, you can easily create a simple remote control. I've ventured into various projects with the ESP32, but a new challenge called for me. It was time to tackle something bigger, creating what I call the ultimate remote control. In short, my goal was to include everything that fascinated me, seemed practically useful, or simply sparked my curiosity to experiment. It may not be the real ultimate remote control in the world, but it will be the ultimate remote control for me. This is the initial structure I had in mind in the early stages. Now here is the final PCB design, which took me about a month to complete. It's time to take a closer look at the functionality of the ultimate remote control I have created. Allow me to walk you through its capabilities. The remarkable thing about using the ESP32 is its wireless control capability. Programming gives you the ability to communicate with the target remotely using methods such as Wi-Fi, Bluetooth, and ESP Now. Or, if you wish, by setting up a software server on the ESP32 side, you can control the target from your PC, smartphone, or tablet screen, all through a web browser. It's like remote control magic at your fingertips. When it comes to building a remote control, joysticks are a must. In my design, I've included 2 large joysticks for a good reason. They are essential. As you may know, these joysticks operate on the X and Y axis, which act like virtual levers. This movement can be used to control anything from moving a toy car back and forth to maneuvering a robot arm. There is also a vertical switch that you can press for additional input. In addition to the larger joysticks, I've added 2 smaller surface mount joysticks right next to them. These compact controls have 5 buttons: up, down, left, right, and center. I've used the same type of joysticks in a previous project with the ESP32 and RP2040. For this setup, I mounted them directly on board. This placement makes sense because these joysticks have a small footprint and do not take up too much space on board. However, due to their small size, they can be a bit tricky to click around. On the top of the unit, you notice a pair of toggle switches, one on the left and one on the right. They can be programmed to toggle between different modes or states of the controller, such as switching from operating mode to configuration mode or menu mode. The other 2 are just for turning the power on and off. Right next to the toggle switches, you'll notice 2 knobs, one on the left and one on the right. During the design phase, I didn't assign any functions to these knobs. They may come in handy for fine-tuning certain settings. Oh, and Don't miss two rotary encoders, one on each side. These little things have a lot of potential. You can use them to control things that require rotation, but you can also use them to switch between menus or navigate through menu items. I have a pair of displays ready to show any useful information for this PCB design. These displays are connected using the SPI protocol, and the UI programming is done using Loveyon GFX. Now, the exciting part is that having two displays opens up a world of possibilities. I can arrange the information I want to show and split it between the displays depending on what I am doing. For example, one display could show you all the real-time action details of the target, while the other display could show different statistics related to what you are controlling. Oh, and here's an idea. With these joysticks on board, I could even turn the setup into a basic game console with a little programming magic. How cool is that? I also designed the PCB to allow a microphone module to be plugged in and easily used when needed. It could be used for voice input. Think about it. With a microphone, I might be able to control targets just by using my voice. Sounds promising. The ESP32 comes with these handy I2S output pins. They are like the communication lines for sending audio data. Here's what I did. I connected a pcbway, an amplifier, and a pair of speakers to the board. Yep, this setup is ready to make some noise. Although, due to its compact size, the sound quality may not be super laudable. With these audio elements in place, this little package could turn into a little device that tunes into your favorite online radio stations. As an experiment, I tried installing two different types of gyro sensors. There's an intriguing possibility with these gyro sensors. Imagine controlling the target by simply tilting the remote. It's a new way to interact. I wanted to try two types of gyros on the board, but I only soldered one. It is the KXDJ31057. It has a library available, so I decided to use it for this project because I thought it would be easier and faster to start with provided library. Given the remote control nature of this project, going battery powered seemed like an inevitable step. It's all about portability, right? Well, here's the interesting part. On another dev board, I came across a neat little chip called the TP5400. It can charge a 18650 battery and pump out 5-volt power from the same battery. But there's a catch. You can't use it as a charging and boosting circuit at the same time. Yes, that's a bit of limitation, and I'll talk more about that later. Given the size constraints of the board and the fact that some of the additional features may not have crossed my mind during the design phase, I wanted to leave some room for future expansion of the functionality. To accomplish this, I've put together 4 different expansion options, all designed to pave the way for potential upgrades and new features in the future. The I2C communication protocol is used by several components on the board. There are so many I2C sensors and modules on the market, and it will be great to be able to use them all on this board via I2C connectors. All of my I2C expansion connectors follow the Groove connector standard. Not only do I have the connectors that are powered by 3.3 volts, but I also have connectors that are powered by 5 volts. This means I can use a full range of I2C modules out there including those from the M5 stack lineup. Not stopping at I2C, I've also set up a dedicated UART port. When the board is all set up, I will experiment with connecting a device called the Husky Lens to this UART port and try out some high-level AI-powered object detection, face recognition, etc. And of course, it can be connected to any module or device using UART protocol. While thinking about the future expansion, I thought it would be nice to be able to plug in any external USB-connected joystick or similar devices. So if there are some fancy USB-connected joysticks or controllers out there, I can use them as a feature extension just by plugging them into the board. To make this possible, I built a circuit using the ESP32 This setup taps into the USB host circuit I borrowed from the M5 stack, and that opens a whole new door of possibilities. Since two joysticks use 4 potentiometers, I turned to the 74HC4051 to help me add more analog pins. With the 2 joysticks and the 2 more standalone potentiometers, you would normally need 6 GPIOs to handle the analog input. But with the help of the 74HC4501, only 4 GPIOs are needed to do the job. Since I am using a large number of switches this time, there are not enough I/O pins for digital input, so I used the MCP23008 to expand the number of GPIO pins. I ended up using up to 3 MCP23008s in my circuit, but the MCP23017 might be another good option. So that's the outline of how the functionality of this project comes together. Considering the size of the board, I decided to take a step-by-step approach. Instead of soldering everything at once, I decided to solder and test each functional block individually. As you can imagine, with all the components and intricate circuitry woven into this board, things didn't always come together as expected. Some parts worked seamlessly, while others had their fair share of bugs and didn't quite work the way I expected. Here are the bugs and failures I experienced with the first version of the PCB. There was a mistake in my schematic. I forgot to connect the common output pin of the 74HC4051, so I cannot receive any analog input. And I also connected pin 2 to ground by mistake, so I2C addressing does not work. Fortunately, I was able to fix the situation somehow. While testing the USB host function, I ran into a roadblock with the USB host circuitry. No matter what I tried, I couldn't get it to work. It turned out that the certain pins were not connected correctly in my schematic, so they were connected incorrectly on the PCB, which caused problems. It seems that the MISO and MOSI were reversed somehow. Realizing that this would be more difficult to fix on the current PCB design, I decided to design a dedicated board for the sole purpose of testing USB host functionality using the MAX3421E chip. This will allow me to isolate the problem and work on it without affecting the main project. I will make a dedicated YouTube video to show you how I built a new board and get the USB host working. So subscribe and stay tuned. I also encountered an unexpected hurdle with the battery charging and 5V supply circuitry. First, the low current capacity of the inductor caused it to burn out on the initial power up. After some research, I found that it could charge the battery and provide 5V, but it couldn't do both at the same time. Again, I decided to build a dedicated board just to test the charging and voltage boosting functions of the TP5400. Early in the design, a misunderstanding that the tab of the LM1117 was a ground pin led to a design error. When I powered it up, the PCB got very hot, alerting me to the possibility of a short circuit. I then realized that I had made a schematic error and that my PCB design was also flawed. I realigned the soldering connections with some heat-resistant tape and a copper wire. This workaround saved my board and allowed me to continue with the project. The KXTJ3-1057 had such a small footprint that I had a hard time detecting it via I2C after soldering, and I had to debug it for quite a long time. Since the circuit of the KXTJ3-1057 was simple, the only peripheral was some decoupling capacitors. It was brand new, so it is unlikely that there was a component failure. So I thought it might be a soldering error. I removed it from the PCB, and as I suspected, I found 4 pins with no solder on them. That's why it couldn't be detected as an I2C device. I applied flux directly to the pins and put the solder on the pins first. Then I soldered it back to the board with a hot air gun, and it worked. As the soldering progressed, a few bugs were discovered as mentioned. But all in all, the board turned out very well, with 80% of the functions I initially expected working properly. I think I can call it a success as an experimental board. Now let's take a look at some of its successful features. The connector that uses I2C also works fine when I connect it and test the M5 stack I2C module, which requires a 5 volts input for power. In this PCB, 2 I2C connectors are powered by 5 volts, as I mentioned before, so the M5 stack I2C modules can also be used without any problem. Besides, I also prepared 2 I2C connectors for I2C modules that use 3.3 volts as power. The mini PBS unit with a QMP6988 was used for this test. After soldering the I2S related circuitry, I ran the source code of the Internet radio I made earlier with almost no modifications, flashed the code to the ESP32, and the Internet radio started playing. Since the I2S and its output amplifier circuit are included, and even the 2 small surface mount speakers are mounted, the Internet radio was easy to implement. Thanks to the circuits I have collected and tested in the past. Also, when programmed as a remote control, it seems to be able to play sound for any operation. The soldering is pretty much done, and once the knobs and other parts are attached, it will be almost finished. Looks more like a remote control now. Now that the hardware is almost ready, the next step is programming. First, I will test the display using Lavion GFX, which is the fastest graphics library the ESP32 can use. It is also possible to use more than one display. Programming the GUI took quite some time. This might be the first time I have done a relatively complete and nice GUI. It's a lot of work, but it's not a waste of time because what I created can be used for future projects. It is a lot of fun to visualize and see the movement of the joystick. The next step is to visualize the movement of the gyro sensor. The position of the circle changes and the left, right, and front back tilt, making it very easy to understand visually. The size of the circle also changes as it moves up and down, so the changes in the height are also represented. The joystick and encoder are now visualized by the GUI program. The next step is to visualize the switches. After days of programming, I managed to get the GUI to give visual feedback all operations of the onboard input components. This is how it works. To send and receive data with ESP now, you need to organize your data structure well. Once this is done, sending and receiving data is relatively easy. Once the receiver can receive data, then it is possible to use that data to control things on the receiver side, like motors, servos, or anything. The other uses data from the gyro sensor to control the robot arm. I still have a lot of ideas about how to use this automated remote control, like controlling a toy car with the husky lens, using your face position or direction to control the toy car, or using your voice to send commands to your toy car or robot. But I don't have all the time to fully implement every single idea to demonstrate in this video, so I will leave them for some time later. Please consider subscribing to my channel so you don't miss any future updates. After this 20+ minute video, I'm sure you have an idea of what my ultimate control is capable of. So I guess that's all for today's video. For future work, I might continue with these steps. Well, I guess that concludes this video. If you find something interesting or find this video informative, please consider subscribing to my channel to see more videos like this. Thanks for watching and see you next time.